Hi, I'm Dan Hannard from Physics Partners, and in this short film, we're going to be looking at how to teach energy stores and transfers. This film is part of a series to help you with your physics teaching, especially if you are new to teaching, new to physics, or just looking for some new ideas. I'll focus on the common misconceptions that students have and give you some tips for introducing the concept, especially if you're teaching remotely. Feel free to pause and take notes, or watch again. So, what would it be like if all of the energy was removed from this room? Energy is one of those words which occur all the time in everyday use, but has a very particular meaning in physics. A task like this gives you a good idea of the starting points of your students. You'll find they say things like, it will be dark, it will be cold, nothing would happen. What would it tell you about a pupil if they responded, everything would be floating? Pause for a moment and consider what misconceptions this student may have. From a response like this, it might tell you that they've previously heard of something to do with energy and gravity, but mixed the two ideas up a bit. So, back to this. What do we use the concept of energy for? Well, we use it to answer questions like these, which all have calculable solutions. The concept of energy is a beautiful, powerful one, but can't do everything, as we'll see shortly. You may have previously taught or been taught yourself about energy in terms of different types or forms of energy. When describing dropping a ball, you may have said something like, gravitational energy is converted into kinetic energy. The issue with a description like this is that it is just labeling of a situation. This sort of sentence tells us nothing about why the ball falls, how it moves, or what might happen in the future. Physics is a way to explain why these things happen and make predictions. Naming types of energy does neither of these. It also suggests that there are different types of energy when there really is just one, just energy. A more useful explanation might go something like this. There is an attractive force between the mass of the ball and the mass of the Earth. The ball accelerates downwards because it experiences an unbalanced force. I've given a clear explanation there of what, why, and how, and not mentioned energy at all. That's because physics is about changes, and changes are caused by forces, not energy. So why do we have the idea of energy at all? We use the idea of energy because it tells us what can happen in a quantifiable, calculable way. We can answer questions such as the ones at the start of this film. Here's a useful analogy. In what way is energy similar to money? Pause the video and consider for a minute. Although the note and the coins are clearly different types of object, the key thing is that they have an agreed common value. £5 is worth £5, regardless of the situation that the money is in. You could spend some of it, all of it, none of it, but not more than it. Money doesn't make things happen, but it tells you what can happen in a quantifiable way. The concept of energy in physics is very much the same. The key idea is that there is only one type of energy, and it can be stored in some different ways. All can be calculated with a formula linking physical quantities in a given situation. Listed here are the main stores to think about at Key Stage 3, although there are others that students will encounter in Key Stages 4 and 5. You might notice the absence of light, sound, and electricity. Now, that is not because they don't carry energy, of course they do, but more to do with the fact that for these listed stores, the one I'm really interested in how much energy in joules is in the store that I can calculate. Whereas for light, sound, and electricity, it's much more useful to think in terms of how quickly energy is being transferred, in joules per second or in watts. Let's put these ideas now into practice using an online simulation. This is one of the PhET simulations from the University of Colorado, which are free to use and can easily be found online. I've included the link at the end of this film. Let's put the skater at the top of the ramp and let her go. As we can see, she falls down the ramp, speeding up, is fastest at the bottom, and then continues, slowing up the other side until she stops, and the whole process repeats. Why does this happen? Well, again, there is an unbalanced force on the skater due to the gravitational attraction of the Earth, so the skater accelerates downwards. Once she reaches the bottom, the force from the Earth's gravity acts to slow her as she moves up the ramp, eventually stopping her. Again, no mention of energy at all. What energy can tell us, though, quite beautifully, are the answers to some specific questions. How fast will the skater go if she starts at a certain height? How high will the skater reach if she's moving at a certain speed? Let's add on a bar chart to show the amount of energy in the kinetic store associated with movement and the gravitational store, here labelled potential. Whilst we watch, ask yourself the questions from the previous slide. What happens to the kinetic bar as the skater gets faster and slower? What happens to the potential gravitational bar as the skater gets higher or lower? What happens to the total bar and why? So we can see here a really clear representation of the idea of conservation of energy. That energy can't be made or destroyed, only shifted between stores, keeping the total value of energy consistent and the same as we have in any system. Now let's look at how to make this situation a little more realistic. We realise that this skater actually wouldn't keep moving forever, eventually she'd slow down and stop. Why? Because there is now an additional force from friction between the wheels and the ramp and the force from the air on the skater, both of which will act to oppose the motion. This extra force will gradually decelerate the skater until she stops. The temperature of the wheels will increase due to the work done by friction. So how is energy involved? As the temperature of the wheels increases, the thermal store increases. As the total energy has not changed, the increase in the thermal store must be matched by a decrease in the kinetic and gravitational stores. A key point to emphasize here is that the thermal store is not making the skater slow down. It is the force from friction that is doing that. The thermal store is a way of accounting for how much of a change there has been. Now, the simulation showed us a continuous process, but the concept of energy is most useful when comparing a change between a clear start and end point. For the skater, we may have chosen the start to be the skater at the top of the ramp, not yet moving, and the end where she is moving fastest at the bottom. You'll probably find that your department has a tray of equipment called an energy circus, full of wind-up toys, torches, radios, springs and things used in the past to label types of energy. A much more useful activity to do with this kit would be to guide students to think about the stores of energy in terms of start and end points. Pause for a moment and consider. What would be useful start and end points to discuss in each of these situations, where a discussion of energy could generate some specific questions rather than just be a labelling exercise? As an example, let's take dropping a ball. Choosing the end point as when the ball just touches the ground would be interesting, but what about having the end point as where the ball is bounced back to its highest point? Energy would let us calculate the speed that the ball leaves the ground by making a measurement of the bounce height. I hope that this short film has been a help in teaching this topic. Below are some links to the simulations I showed you and some other useful resources. Hope to see you again soon. Goodbye.